Hello, everybody. Welcome back. Today, we're going to be talking about stereochemistry again, but we're going to be diving into enantiomers and diastereomers. And so these are two very important terms that we're going to be looking at to actually define how two things are related to one another. So the first one that we're going to define is what is an enantiomer? And as a matter of fact, we have defined an enantiomer multiple times in the previous lesson. So an enantiomer is just a non-superimposable mirror image, right? And we were looking at those a lot last time whenever we were doing this. So to bring back everybody's favorite compound from the previous lecture, it was the one that we started out looking at. It's the one that we ended with looking at. It's this one here. And so you will probably remember that the mirror image of this one is a little different from what we just drew because, as a reminder from the previous lecture, we ended up doing some rotations and proving that these are non-superimposable. The other thing we took a look at was the fact that if you labeled these based on their priority numbers and did some looking at their absolute configuration, what you'd find is that this one was S, and that this one over here was actually R, right? And so knowing the definition of an enantiomer being a non-superimposable mirror image, and us having talked about this last time, you may immediately notice that if two stereocenters are opposite configurations, they are enantiomers, right? Because that's just the way this has to be. If one of them was S and the other one is R, those are opposite absolute configurations. These are non-superimposable mirror images. Therefore, they are enantiomers. So that's one way that we can actually define these. Okay, and so these enantiomers, these non-superimposable mirror images, have the same physical properties, right? And so if you think of a physical property, right, this will just be another flashback to Gen Chem. We're talking things like boiling point, melting point, density, stuff like that, right? However, they have vastly different biological properties. And I think there's a really cool molecule that demonstrates this really, really well. And that molecule is actually one that you are familiar with. You just don't know how familiar you are with it at the moment. This right here is methamphetamine, also known as the drug meth. And methamphetamine, you'll notice if we were taking a look at this and I asked you if it was chiral, you could probably look at it and point out that, hey, this carbon right here has four different things connected to it, right? It has the hydrogen that we didn't have shown. It has the CH3 there, has this nitrogen with that chain right there, and it has that CH2 with that big chain right there. So this is chiral. And as such, all chiral compounds, as we saw last time, have two different ways that you can draw them, right? One of them is where that methyl group is on a wedge, and the other is where that methyl group is on a dash. Okay? So if we have methamphetamine now split up into these two different isomers, we can say that, hey, these are enantiomers of one another. All right. And the reason that we know this is because if we were to do some absolute configuration, let's just throw in the hydrogen right there, right? Nitrogen would be number one in priority because it has the highest atomic number. Then that carbon chain is bigger than CH3. And then, of course, the hydrogen is in the back. Looking at that rotation, we see that's counterclockwise. So this is S methamphetamine. And then the molecule on the right, where it has that hydrogen on the wedge. I'm not going to go through and draw the full thing. Just remember that just like with the right hand rule, if you're using that, this is one, two, three, and four, right? It's rotated and it's looking like it's counterclockwise. But keep in mind if the wedge or if the hydrogen is on the wedge, number four, it is the opposite. So this is R methamphetamine. And as I just described, these are enantiomers to one another, right? And the reason we can say that is because we know that if two stereocenters are opposite configurations, they are enantiomers, and that means that they are non-superimposable mirror images of one another. So the thing about these enantiomers, though, is that physically they have the exact same properties. But in a biological system, like your body, they have very different properties. For example, the one you may be very familiar with is S-methamphetamine, right? This one has that strong dopaminergic response, right? It is the one that quote unquote gets you very high. All right. On the other hand, our methamphetamine, funny enough, is Vicks VapoRub active ingredient. Odds are you have actually come in contact with methamphetamine in your life before, right? Because it is a very good nasal decongestant. And so it just goes to show that these two compounds, even though they look incredibly similar and they have the same physical properties, they perform very differently in biological systems. That being said, if you want to see some other drugs that are kind of like this, see book page 229 for some other examples. Okay? So, meth isn't always a bad thing. All right? It depends on which enantiomer you take. Now, that being said, we actually have to keep in mind how we identify some enantiomers, right? And so to do so, we need to start getting used to what enantiomers look like and how we can tell the difference between them. So we're going to look at three ways to identify enantiomers. Oh, whoops. And we're going to start out with the very simple first way, which is the one that we've been using multiple times, which is checking the absolute configuration. Right? The important thing about this method is that, funny enough, it always works. This is why when I explained absolute configuration last lecture, I said that if you understand how to do absolute configuration, everything is going to be easy for you. Okay? So, looking at this, let's say we looked at two different molecules. We look at one that looks like this versus one that looks like this. Very similar in terms of they have the same connectivity, they have the same molecular formula, but we can see that what's on the wedge or slash the dash is a little different in each. So looking at the one on the left, we have to first draw in this other hydrogen, right? So that we can start labeling things for absolute configuration. And the first thing we need to do is we need to make sure that number four is on the back. And hydrogen's always the smallest, so it needs to go towards the back. So we actually need to do a little bit of a rotation. So if we were to rotate this 120 degrees, we would see that, alrighty, we have now the methyl group where the hydrogen was on the wedge. We have the hydrogen now on the dash where the alcohol was, and now we have the alcohol on this in plane space. Now then, if we were to label these based on priority, we would see this is our one, two, three, and four. Because remember, for the oxygen, it takes highest priority. The hydrogen takes lowest priority, just due to atomic number. Looking at the two carbons that are connected, They have the same priority, so we have to move another atom out. The one that we now have labeled 2 has that carbon attached to it, whereas the other one only has 3 hydrogens, and since that carbon is larger, it is going to take our second position. So then if we draw our arrow from 1 to 2 to 3, that is counterclockwise, so this is S. On the other hand, for this one over here, we also have to draw in that other substituent is a hydrogen. So we do need to rotate that one to the back where that methyl group is. So this is going to be a very similar rotation, 120 degrees. Keep in mind you could use the right hand rule for this if you wanted to. I am not doing so just for the sake of keeping everyone who doesn't want to use that in the loop. So we have this right here. That tells us that oxygen's 1, 2, 3, and 4. It's the same numbering as last time in terms of what has priority. They've just changed positions. So there's our rotation. We can see that as clockwise. So this is R. And as we said before, if these two are opposite, they are enantiomers. So this is one way that we can identify if something is an enantiomer. There are two other quick ways, though. All right. The first one is what we're going to list as our second overall way of checking, which is what I will call wedge becomes dash. All right. So what this looks like is essentially if we have a substituent on a wedge and we're comparing it to something where that same substituent is on a dash, the fact that these are opposite means that they are enantiomers. All right. So this is a very quick way to do it. If you do not believe me on the fact that these are opposite means that they're enantiomers, we can resort back to checking the absolute configuration to make sure that is true. Right? Let's take a look at the absolute configuration of these. We see 1, 2, and 3. The hydrogen, which is on number 4, right there. This one is R. Looking at the one on the other side, since it's on the dash, keep in mind the hydrogen is now on the wedge. You can do the rotation for this, or you can use the right hand rule, which I'm going to use here because it is interchangeable. It looks like it would be R, but keep in mind, since the hydrogen, which is number 4, is on the wedge, it is opposite. This is S. We see that these are now opposite, which means they are enantiomers, right? So notice how even if you don't pay attention to this wedge becoming the dash, you can still do it using absolute stereochemistry. Now keep in mind absolute configuration again takes a little bit of time. So if you're able to do it with the wedge becomes a dash, it's going to be a little faster for you. Another one that's also very fast is our third option, which is that they are just actual mirror images. And so this one's easy to identify because essentially when you look at one of these, you'll see that the way the other molecule is drawn is the same way that you would draw it if you were to just put a line in here as a mirror image. If you see this right here and they are chiral, you know that these are enantiomers, right? Because enantiomers are just non-superimposable mirror images. If you don't believe this, you can actually do some movement to check and see if it's true. So let's say that we decided to flip this molecule around an axis like this, right? A whole 180-degree flip over. What you would see is that now the oxygen would be on the left-hand side, and while it was on a wedge, we've now rotated that 180 degrees, so it's going back into the page. It is now a dash. All right. This is where method 2 once again comes in handy. Because check these out, right? These are opposite. That tells us that these are enantiomers. You still don't believe it? Well, as a matter of fact, you can go ahead and you can try and do some absolute configuration. You'll once again find that this is R and this is S, right? So essentially, each method works and is backed by the other methods. But the one that will truly never fail you, because keep in mind, you could accidentally flip this and do it incorrectly. You could accidentally not notice that the wedge becomes a dash. I don't know how you do that one accidentally, but essentially, if you know your absolute configuration, it always works as long as you don't make a mistake in terms of labeling your absolute configuration. Now then, we've been looking at these enantiomers, and those are three good ways to identify them. But the question then becomes, you've noticed that for each of these, we're kind of labeling on one chiral center. What about multiple, right? What about multiple chiral centers? Well, of course, this is where things get a little interesting because let's take, for example, this molecule right here. Okay? Looking at this, if we were to label this with some absolute configuration, right, we would see that, all right, I'm going to draw this a little bigger so that we have all the atoms shown because there are some hydrogens that are on dashes that I didn't have shown before. Okay, so looking at the one with the chlorine, chlorine is the highest atomic number. That carbon would be 2, the CH3 would be 3, that would be 4, right? This is rotating clockwise, so that tells us that this is R. The bromine, on the other hand, bromine would be number 1, that carbon would be number 2, there's number 3, and the hydrogen's number 4. Rotating around, since the hydrogen's in the back, we're all good. It's counterclockwise, that is S. All right. So looking at our original structure up here, where we have our R and our S, we know that if we drew a structure that had these swapped, that it would be the enantiomer, right? The easiest way to do this is, of course, to also think about if our wedge becomes our dash, right? Because now the stereocenters, if you were to do your absolute stereochemistry, have also swapped. So these are enantiomers. All right. You could also draw them in a different way, right? If you were to draw it where you just draw the actual mirror image, right? So there's our mirror, and then we draw in what it would look like if it's looking at itself in its reflection. These are also enantiomers. Which, by the way, if you think about that, that means that these two things are actually the same molecule. They're just a rotation away from one another. But here's the thing that you might have noticed. If you have multiple chiral centers and we're changing both of them, that makes enantiomers. But what if only one changes, right? What if only one wedge slash dash changed? Well, interestingly, this creates a new type of stereoisomer, right? Looking at if only one of these changed, let's look at that original molecule again, right? So we know that the chlorine was R, the bromine was S. Let's say that we swapped one of them and we just decided to do the chlorine and we kept the bromine on a wedge. Well, what we see now is the chlorine is now R, stereochemistry. The bromine is now R, and these are not enantiomers, right? Because essentially they can't be enantiomers because only one of them changed, but not all of them. These are what we call diastereomers, right? So these are diastereomers. And what these are is just essentially a stereoisomer that is not a mirror image. Right? Everything we've been looking at so far has been mirror images. This is an example of when something is not a mirror image. But the only time this can occur is when you have more than one chiral center, right? And so the secondary definition I want you to think about for diastereomers is that some, but not all, configurations are different. All right? Because remember, if all of the configurations are the opposite, it's just the enantiomer. If some but not all of them are opposite, it is a diastereomer. So knowing this, we've actually created a very interesting dynamic here, right? Because we've listed out a couple of relationships now that are very important. We said that this molecule right here, right? If we were to compare it to another molecule is an enantiomer, right? So we can make the enantiomer of this molecule, which is just swapping the stereochemistry of both of those carbons, right? Because this is R and S, and now this one is S and R. Now then, another thing that we see is that we've also changed only one stereo center here, and those are what we call diastereomers. But what you may have also noticed, right, because we changed the chlorine but left the bromine, what you'll also notice is that's not the only diastereomer we could have made, right? What if we swapped the bromine but not the chlorine? Well, let's draw that down in this little corner over here. So if we kept the chlorine the same, keeping it on a wedge, and we put the bromine on the dash, we have the diastereomer of the original molecule we drew. And funny enough, the reason I set these up like this is because you'll notice that some more relationships start to form. For example, if we take a look at the right-hand side, the two things that we have drawn here are diastereomers, right? Because if we're labeling our configurations, right, this one down here is S and S, and looking up there, the chlorine is S, but the bromine is R. Wait, I did this. Oh, sorry, I labeled that incorrectly. Should be the opposite. So it should be RR here. So the chlorine up top is S. Now the chlorine on the bottom is R, right? So it's opposite. And this one over here is SS, which is why it's diastereomers of the one above it. Now then, although those are diastereomers, the SS and the RR are also related, right? They are enantiomers of one another because all of the stereochemistry has changed there. And then even more interesting, on the diagonal once again, those molecules are diastereomers of one another because the SR and the SS only has one stereocenter changed. So essentially, what this is telling us is that all stereoisomers are related by these terms. So if you can understand what an enantiomer is, and if you can understand what a diastereomer is, you will be able to kind of figure out what all of the different types of stereoisomers something can have. So as a reminder, the easiest way to think of these is that for enantiomers, all configurations change. And then for diastereomers, some, but not all configurations change. Now, one thing I want to make very obvious for everyone is that remember that these are just stereoisomers. Not everything is a stereoisomer. Okay? Some things can be constitutional isomers. You have to keep these things in mind. And we're going to do a whole lecture about relationships between things in just a little bit. But just keep these things in mind when you're looking at this is that these two terms only refer to stereoisomerism. Okay. Now then, an interesting thing about these diastereomers, right? Because keep in mind, we were talking a little bit about them before we got into this conversation here, is that they do have something different about them in comparison to enantiomers, right? And that is that diastereomers actually have different physical and chemical properties. All right, so unlike the enantiomers that we were looking at that only really made a difference when we're talking about biological systems, these actually have vastly different physical properties. So if you were to compare, for example, this structure versus its diastereomer, where we changed that bromine to be on a dash, you would see that these have different boiling points, densities, all that stuff. Right? And not only that, but they also have different biological properties. All right, so essentially, they kind of act like they are different molecules entirely, despite being the same molecule, just with a different stereocenter orientation. Okay? So that's something else to keep in mind about these things. Now then, the next thing that we got to worry about is that we've talked about there being a couple stereoisomers, right? So we've looked at enantiomers, we've looked at diastereomers, but one question remains, which is how many stereoisomers does a molecule have? And well, this question is actually very easy to answer. It depends on the number of stereocenters. Okay? So let's take a look back at a molecule that we looked at many, many times before. It has come back once again. When we looked at this molecule right here, and we asked how many stereoisomers exist of this. Now, keep in mind, we do count this as one of the stereoisomers. It has one stereocenter and two stereoisomers, right? Because other than this one here, which is the S enantiomer, it has the R enantiomer, and that's it, right? It doesn't have any diastereomers. It doesn't have anything else. It's just the R and S enantiomer. But then as we moved on to this right here, right, this one had two stereocenters. And you notice that when we were filling out that chart, it has four corners, right, for all the four different stereoisomers. So this one has four stereoisomers. Okay? So the question becomes what happens if we have a third stereocenter? So let's take an example of something that you might see as a chair conformer, right? For something like this, looking at it, we have a stereocenter there, there, and there. For three stereocenters, if you were to draw all of these out, you would find that it is eight stereoisomers. So when we ask ourselves the question of how many stereoisomers there are, essentially there's actually a very easy answer that can be calculated, and that is it is actually 2 to the n equals our number of stereoisomers. And in that, the n is equal to the number of stereocenters. Okay? So what this means is that when we look at this idea of stereoisomers to stereocenters, right? If n is increasing, so we have one, two, three, four, five. Let's just, yeah, let's take it out to five. Then our number of stereoisomers is also going to be increasing, right? Because doing the calculation here, 2 to the 1 equals 2, 2 squared equals 4, so on and so forth until you reach 2 to the 5th, which, if you do the math there, should be 32. So, with that being said, this is a relatively exponential equation that grows depending on the number of stereocenters you have. All right. So keep that in mind whenever you're asked to draw multiple stereocenters. Always check and see how many should you be drawing. Is it 8 because you have 3 stereocenters? Is it only 2 because there's only a single stereocenter? It depends. Okay, let's move on to the last little thing of this lecture, which is what we call mesocompounds. And in undergrad, these were the bane of my existence, right? Because these guys are a little tricky to identify. And the reason is because of our definition of chirality, right? So as a reminder, we had defined chiral previously as a molecule that is not superimposable with its mirror image. Okay? Essentially, what we have said by stating this definition is that a chiral molecule has an enantiomer, right? That is kind of the definition that we've given. So, what is a mesocompound? Well, a mesocompound is a molecule with stereocenters, but is achiral due to being superimposable with its mirror image. Which at first sounds really strange. But essentially, what we're saying about a mesocompound, right, in this little thing that we can say, AKA, it has no enantiomer. And I think this definition right here is really useful whenever you're thinking about this exact idea. So let's take a look at something that is a mesocompound. And it is going to be this right here. So for this compound, if we were to try and draw the mirror image of it, right? We were trying to just take this and draw the mirror image directly as it stands. You would find out that it's kind of weird because nothing changed, right? If this thing was looking in the mirror, it is the exact same. Okay? That tells us right away that there is no enantiomer. But you may say to yourself, oh, but what if I were to take this and I said, ignore the fact that I'm drawing a mirror image. What if I just change the stereochemistry? Now this looks different, right? Well, it does look different, but there's one issue that we have, right? Let's say we were to take this and we were to flip it. If you flip it 180 degrees around this axis right here, you would find that the oxygens that were once going back into the paper are now coming out towards you. And would you look at that? It looks the exact same as the start, right? These are the same. And as such, the enantiomer doesn't exist. Okay? So what we're saying here, whenever we're looking at these mesocompounds, is that the enantiomer is the exact same as the original. If the enantiomer is the exact same, it does not exist. Let's take a look at one that's a little more tricky because this one is pretty obvious whenever you first look at it, right? Just drawing out that mirror image was immediately telling that it was not actually a real enantiomer. But for this one, it's going to play a little bit harder of a role. Let's draw the mirror image of this here. Well, for this one, right off the bat, it does not look particularly different, right? Or I mean, well, it looks different. It doesn't look particularly the same. It looks like an enantiomer. However, you may notice something. If you take this right here and you were to do a couple of flips, what you would find is that you end up in the exact same scenario, right? To show this, what we can do is we can actually just do a single flip. Across this horizontal axis here, if we were to do a 180-degree rotation, we would find that that bromine that was going back into the page is now coming out towards us. The bromine that was coming out of the page is now going back into it. These look the same. You can probably tell by now that, by the way, I didn't label these beforehand, but these, of course, are miso. And this, of course, is miso. So you can probably tell that even if we tried to do the trick of swapping the stereochemistries rather than drawing the mirror image, that you wouldn't have any luck, right? These molecules right here that are both miso are somewhat hard to identify, right? You kind of have to draw out the mirror image of it to make sure. But there's one thing they have in common, all right? And what they have in common is a mirror plane, aka a plane of symmetry. All right? If we were to take a look at the first molecule, let's redraw it out. It has a very obvious plane of symmetry, right down the middle. The other one, though, is a little bit more hidden, I'll call it. Right? Because looking at this guy, this clearly is not showing a mirror plane. But interestingly enough, if you do a little bit of a rotation around this bond here, right? And this rotation would actually be a rotation to form an eclipse conformer. What you'd see is this right here. And wouldn't you know it, a very nice, easy, symmetric mirror plane cutting down the middle. It is true that all meso compounds are symmetric. They all have a plane of symmetry right in the middle of them. However, you can also identify them by seeing if they do not have an enantiomer. Here's the interesting part as well, though. They may not have an enantiomer, but they do have diastereomers, right? If we were to take that same first example that we were looking at again, and we were to change one of these from a wedge to a dash, right? Let's say the one on the right here, we would have what are effectively diastereomers, right? Same thing with if we changed it in the opposite way, right? We can also have some diastereomers where we just changed instead of the one on the right, the one on the left. Of course, these diastereomers are related to each other as they are enantiomers themselves, which is a really weird thought because it is true that meso compounds do not have enantiomers, but their diastereomers do have enantiomers, funny enough. But the main important thing is that it itself does not have an enantiomer. And so whenever you're looking at this equation that we put up here, right, where it's 2 to the n for meso compounds, right? The number of stereoisomers is 2 to the n minus 1, right? And so that minus 1 is essentially signifying this is your lack of an enantiomer. So, with that being said, that is everything for today. So hopefully you were able to get out of this lecture the difference between enantiomers and diastereomers, and maybe you got a little bit of an idea of what these things called mesocompounds are. Going through the rest of stereochem, we're going to start looking at relationships between compounds. We're going to start taking a look at a little something that is called optical activity that also relates to these enantiomers. We'll see you next time.